And so you guys got the right approach. My guess is it's in your pacing. The answer is pretty close to 400 to 500,000 years before present. So in thinking about what we've done there in making that calculation of how old a flowing stone of time is, it's a really big assumption that that growth rate that we've measured on those 40 centimeters is applicable to the whole period of growth, right? It could have been much faster, it could have been much slower. Just the mere fact that we say we'd like to use these changes in growth rates to look at past periods of drought, that tells us right there that the growth is not constant, that there's periods it's growing really fast when it's very wet, periods when it's very slow. But that's, based on the information we have, that's the best we can do, and that's a ballpark. So as talking before, it's something we like to call arm-waving geology, taking a little bit of data and making big sweeping conclusions about things. Well, that's kind of the fun of it, just as long as we know that that's what we're doing. I wouldn't publish the age of the flowing stone of time as 400,000 years. As long as you know what your caveats are, you'll be fine. All right, so now we're about to go to the off-trail part, and so we want to make sure that our gear is working. So just make sure your headlamps are working. It'd be a good time to put your helmet on. Pull your knee pads up. Wheels up. We're going off the runway. All right, who's coming next?
Me.
State your name.
Max.
All right, Max. Keep it coming. This is sort of an indicator, these conduits that we're walking through, of where the groundwater has flowed in the past. And you probably had, at some of these levels, a pretty typical sort of shape of passageways is sort of this elliptical shape. These things, like they reach out underneath and they come back. If you were to do this experimentally and try to dissolve calcite at a water table, you would get that elliptical shape, right? To where this may have been where the fracture was. The fracture got widened, and then the dissolving activity of the groundwater and dissolve things out as you went either side of the fracture, and then it would peter out. So you see what I'm talking about? This elliptical cross section is probably telling us we're at a place where there was one time was the water table that was doing this excavating. There's some places as we go forward that you could even imagine there was an underground stream in some of these passages by the erosive activity, both physical and chemical erosion. So we're now going to go forward, and if in caving parlance, a lot of people go caving to explore new places, and sometimes you just have an idea that there may be a new passage, maybe by the air currents that are coming out of a very small hole. You see big air currents coming through it. That means there's a big volume of air on the other side. And so people try to maybe go through and widen that so they could barely squeeze through and see how big that's called pushing a lead. The lead is this evidence that there's more, and pushing it means you're trying to see actually where it goes. In all my years of caving, I've never been one to push a lead, right? Because there could always be a bear or a jaguar on the other side of the lead. I've swam through sumps without any scuba gear in the Caribbean. I'll tell you about that sometime. Not much of a story, except that I dived through a sump without any scuba gear. But I made someone go first to prove that and then come back to prove that it could be done. Okay, so Carly, how about going first?